Bismillahirrahmanirrahim. Assalamu alaikum students. I hope you found the previous lecture helpful and I hope you understood all the topics that were discussed. Today we are going to study the biophysics of circulation. The topics that we are going to discuss today are flow and resistance of blood during circulation. Pressure will later be discussed in detail in the unit of kidney. First, let us discuss the flow of blood in the circulatory system. To calculate the flow of blood through a blood vessel, you must remember the Ohm's law. The Ohm's law states that flow is equal to the gradient of pressure or the pressure difference along a blood vessel divided by resistance. The gradient of pressure is the pressure difference between the two ends of a vessel, whereas resistance is the impediment to blood flow through the vessel. As you can see from this formula, blood flow is directly proportional to the pressure difference and inversely proportional to the resistance faced by the blood while flowing through the vessel. This is the figure showing the pressure gradient at the two ends of a blood vessel. As can be seen in this figure, P1 is the pressure at the proximal end of the vessel, while P2 is the pressure at the distal end of the vessel. The pressure gradient or pressure difference can be calculated by subtracting P2 from P1. While resistance is faced by the blood throughout the length of the vessel. These are some extensions of the Ohm's law. By rearranging the Ohm's law, we may get different algebraic forms of the same formula. While flow is directly proportional to the pressure difference and inversely proportional to the resistance, to calculate pressure difference along a blood vessel, Ohm's law can be distorted such as that delta P is equal to flow of the blood multiplied by resistance faced by the blood during the flow. While calculating the resistance, this formula can be used in the form as resistance is equal to pressure gradient divided by flow of the blood. Blood flow is defined as the quantity of blood that passes through a given point in the circulation in a given period of time. The value of blood flow is expressed as milliliters per minute or liters per minute. Scientists have devised multiple methods to estimate the blood flow through a blood vessel. One of such methods is the electromagnetic flowmetry. To estimate the blood flow by this method, the blood vessel through which the blood flow is to be estimated is exposed and placed between two poles of a very strong magnet. Then, two electrical electrodes are placed on the opposite sides of this blood vessel. The placement of the electrodes must be such that it is perpendicular to the fields of the magnet. When the blood flows through the blood vessel, an electric current is generated. This current is then picked up by the electrodes and can be quantified using any appropriate voltmeter or electronic recording apparatus. The electric current generated is directly proportional to the rate of blood flow. Another popular method used to study the blood flow is known as the ultrasonic Doppler flow meter. In this method, a probe is placed over the blood vessel through which the blood flow is to be measured. This probe contains a crystal. This crystal, when energized, transmits an ultrasound at a frequency of several 100,000 cycles per second. This sound is reflected by the red blood cells flowing in the blood. The ultrasound waves reflected back from the RBCs are picked up by the probe. These waves, which are now reflected back, have a lower frequency than the wave which was initially transmitted. This is known as the Doppler's effect, and it can help calculate the flow of blood through a blood vessel. Now let us discuss the types of blood flow. There are two types of blood flow, laminar and turbulent. Laminar blood flow is also known as streamlined blood flow. What is meant by streamlined blood flow is that each layer of the blood stays at the same distance from the vessel wall. This might sound confusing. Let's look at a picture to get a better idea. Here you can see a blood vessel through which blood is flowing in multiple layers. As you can see that all the layers are moving in a straight line, and the blood from one layer does not cross over to the second layer. To better understand the laminar blood flow, let's take an example of a well-organized traffic flow on a highway. In a well-organized and orderly traffic flow on a highway, all cars move in their lane. No car leaves its lane to enter another lane. And in this way, an orderly and straight traffic flow is maintained. This is exactly what happens in the laminar blood flow. As you can see that the profile of this blood flow is parabolic, which means the layers at the center move the greatest distance or have the greatest speed of movement. The reason for this is that closer a layer to the vessel wall, the greater there is friction between the layer and the vessel wall. As the layer moves away from the vessel wall, the friction reduces and the speed increases. So as you can see in this figure, the layers which lie closest to the vessel wall face most friction. Thus, they are the slowest. As you move away from the vessel wall towards the center of the vessel, the friction reduces and the speed increases. That is the reason the flow shows a parabolic profile. By parabolic profile, I mean the shape of a bullet. Now let's move on to the turbulent blood flow. Turbulent blood flow is disorderly blood flow when it passes through any obstruction, a rough surface, or a sharp turn in a blood vessel. Turbulent blood flow makes whirls in the vessel. These whirls are known as eddy currents. To understand this concept, let's look at this picture. As can be seen in this figure, the blood is not flowing in straight line like that in the laminar flow. In fact, the blood is moving in all directions in a haphazard manner. This results in the mixing of blood and the mixing of layers, causing whirls within the blood vessel, which I mentioned before are known as the eddy currents. You must remember that when there is turbulence in the blood flow, the resistance to blood flow increases. To measure turbulence within a blood vessel, you must know what is the Reynolds number. Reynolds number is the measure of tendency for turbulence. What this means is that Reynolds number gives you an idea of the probability or the tendency of turbulence to occur within a blood vessel. The formula for Reynolds number calculation is velocity of the blood flow multiplied by diameter of the blood vessel multiplied by density of the blood divided by viscosity of the blood. Density is denoted by the Greek alphabet rho, while viscosity is denoted by eta. Dear students, please remember this is not P and N, as many of you make this mistake during the vivas. Now let's move back to the formula and see how each of these parameters affect the Reynolds number. Reynolds number is directly proportional to velocity, which means as the velocity of blood increases, the chances or tendency of turbulence increases. To remember this fact, please bring to your mind the example of a car on a road. As the velocity or the speed of the car increases, there are more chances for this car to skid and move out of its lane and move into the lane of other cars, causing turbulence. Same is the case with blood. As the velocity of blood increases, the chances or tendency to turbulence increases. Now let's see the effect of diameter on turbulence. Diameter of a blood vessel is directly proportional to turbulence. As the diameter of the blood vessel increases, the chances or tendency of turbulence increases. Again, bring to your mind a vast or a large highway. On a broad highway, there are more chances for a car to move out of its lane and enter other lanes. While the same car, while moving on a side lane or a small road, does not have any chance to move out of its lane, as it is probably a single lane road. So as the diameter of a blood vessel increases, the tendency of turbulence increases. Now let's study the effect of density on blood flow. As the density, which is mass per unit volume, increases, the turbulence in blood flow increases. Again, To remember this, picture a highway with many cars traveling. As the number of cars increases, the traffic becomes haphazard and there are chances of more cars leaving their lanes trying to overtake each other. Same is the case with blood. As the viscosity of blood increases, the turbulence of blood flow increases. To understand the effect of viscosity on turbulence, let's remember what is the definition of viscosity. Viscosity is the friction between the layers of a fluid. Viscosity is inversely proportional to turbulence. To understand this, let's go through an example. Here you can see two fluids. Both of these fluids have different viscosity. The fluid in the first panel is olive oil, which has low viscosity, while the second fluid is honey, which is highly viscous. Now imagine trying to pour olive oil into a vessel. As you must remember from your experiments in the kitchen, that while pouring oil into a vessel, you may experience splashing. This splashing or turbulent flow is due to the low viscosity of the oil. Now bring to mind what happens when you pour honey into a vessel. Honey, having high viscosity and friction between its layers, does not splash. In fact, it falls in folds. This is the difference between low viscosity and high viscosity and its effect on turbulence. Now moving back to our formula, as the viscosity increases, like in honey, the turbulence decreases. Now let's have a look at the conditions that cause turbulence. As I mentioned before, that high velocity of blood may give rise to turbulence. Pulsatile nature of the blood flow may also result in turbulence. Turbulence increases when there is a sudden change in the diameter of a blood vessel. Larger vessels have more turbulent blood flow. When the Reynolds number is 200 to 400, there is no turbulence within the straight blood vessel, but some turbulence might be experienced at the branches of the arteries. But when this number rises to 2000, turbulence may even occur within a straight, smooth blood vessel. Here we have completed the study of blood flow. Now let's move on to resistance. Resistance is the impediment to blood flow within a blood vessel. It is actually the friction faced by the blood while moving through a blood vessel. Resistance is calculated using the formula R is equal to delta P over F. Here delta P denotes the pressure difference between two ends of a vessel, while F denotes the blood flow through that vessel. If both delta P and F are taken as 1, then R, or resistance of blood flow through that vessel, is taken as 1 PRU, which is the basic unit of resistance. PRU stands for peripheral resistance unit. As calculated by the above formula, the resistance of the systemic circulation, also known as the total peripheral resistance, is calculated to be 1 peripheral resistance unit. The resistance in the pulmonary vessels is calculated to be 0.14 PRU. Here you can see the stark difference of resistance in the systemic circulatory T and the pulmonary circulatory T. The resistance in the peripheral circulation is many times greater than the resistance in the pulmonary circulation. Factors which affect resistance are the radius of the vessel, the length of the vessel, and the viscosity of blood. The formula which is used to calculate resistance, keeping in mind these factors, is as follows. R is equal to 8 eta L divided by pi R4. In this formula, 8 and pi are constants, while viscosity is denoted by eta and length of the vessel is denoted by L and radius of the vessel is denoted by R. As can be seen in this formula, resistance is directly proportional to viscosity of blood. As the blood becomes more viscous, the friction within the layers of the blood increases and overall resistance to the blood flow increases. Now, what is the effect of length of vessel on the resistance? As the length of the vessel increases, resistance increases, because now the layers of the blood have to cover a greater distance. What is the effect of radius of the blood vessel on resistance? As can be seen from this formula, radius is inversely proportional to resistance. As the radius increases, resistance decreases. But let's not ignore the fourth power of the radius. This means that 1 unit decrease in the radius increases the resistance by 4 times. Let's discuss this in greater depth. As mentioned before, small changes in the vessel diameter or radius markedly change its resistance and flow. The rate of the blood flow is directly proportional to the fourth power of the radius of the vessel. Dear students, please do not be confused by radius and diameter. Here, it means one and the same. Blood flow is directly proportional to the fourth power of the diameter. Thus, it means resistance is inversely proportional to the fourth power of the diameter. It is the diameter of the vessel among all other factors which plays the greatest role in controlling the blood flow. And this is the basis of increasing and decreasing the circulation within a tissue when nervous signals constrict or dilate a vessel. By simply constricting or dilating a vessel, the blood flow through that vessel can be changed to about 256 folds. To understand the effect of diameter on blood flow and resistance, let's look at this picture. In the first blood vessel having larger diameter, the blood which is flowing near the walls of the vessel is slow. This is due to the greater friction between this layer and the vessel wall. But as we move towards the center of the blood vessel, the flow becomes more rapid owing to decreased resistance. Now look at the smaller vessel. In this small vessel, all of the blood is in contact with the vessel wall. So, the overall flow within this blood vessel is slow due to greater resistance. Now let's have a look at the Paslees Law. Paslees Law is a sophisticated formula to calculate the flow of blood through a blood vessel. Previously, we used the Ohm's law to calculate the flow of blood. Since the Ohm's law is simple and it states that flow of the blood is directly proportional to pressure difference divided by resistance. In the previous section, we calculated the resistance of blood flow within a blood vessel. The formula showed that resistance is equal to 8 eta L divided by pi r raised to the power 4. Now let's substitute this value of R within the Ohm's law. By doing so, we get a formula which states that flow is directly proportional to the pressure difference along a blood vessel multiplied by radius raised to the power 4 divided by viscosity of the blood and length of the vessel. This is known as Paslees law. According to this law, the flow of the blood increases when the pressure difference at the two ends of the blood vessel increases. The blood flow also increases when the radius is increased. And this increase in the flow is 4 times for every unit change in the radius. The blood flow decreases when the viscosity of the blood increases. This is due to greater resistance. Also, the blood flow decreases when the vessel length increases. Now, let's have a look at the resistance of blood vessels in different circuits. There are 2 types of circuits, either series or parallel. The blood vessels in series are attached end to end, while the blood vessels in parallel circuits are attached side by side. In a series circuit, the blood vessels are attached end to end. The total resistance of this circuit will be the sum of resistances of each blood vessel in that circuit. To understand this, let's take an example of aorta. Aorta is divided into multiple parts. All of these parts are arranged in series. The first part is ascending aorta, which is connected to the arch of aorta, which is connected to descending thoracic aorta, which is connected to descending abdominal aorta. Now, the resistance of total length of aorta is the resistance of ascending aorta plus the resistance of arch of aorta plus the resistance of descending thoracic and abdominal aortas. While looking at this formula, it is clear that if resistance is added in a circuit, the total resistance of that circuit increases. Now let's have a look at parallel circuit. In a parallel circuit, the blood vessels are not attached end to end. In fact, they are attached side by side. The example of parallel circuits within our body are the branches of aorta. As you can visualize in this figure, that these branches of aorta are arranged in parallel. Now, coming back to the formula for parallel circuits, we can see that there is an inverse relationship between the resistances in the circuit. What does this mean? This means that if you add a blood vessel to a parallel circuit, the overall resistance of that circuit decreases. This is quite opposite to what happens in a series. When you add a blood vessel in the series circuit, the total resistance increases, while this is not the case in parallel circuit. What is the reason for that? The reason is quite simple. When you add a blood vessel in a parallel circuit, you are providing an alternate route for the blood to flow. Suppose a circuit had 3 vessels previously, and now you introduce another vessel. So the blood which was previously flowing in 3 vessels is now flowing in 4 vessels. Remember that in our body, multiple organs are placed in parallel circuits to each other. For example, brain, kidney, muscles, and heart, they are all arranged in parallel to each other. Therefore, the surgical removal of an organ, for example a kidney, will also remove a parallel circuit, thus increasing the total peripheral vascular resistance. Now let us study the effect of blood hematocrit and increased blood viscosity on resistance and blood flow. If you do not remember what hematocrit is, let me remind you, hematocrit is the portion of blood which is comprised of RBCs. This means if you allow the blood to settle in a test tube, the blood separates into 2 parts, the clear serum and the cells. These cells are about 40% of the total blood, and this is known as the hematocrit. As the hematocrit increases, the viscosity of the blood increases, and with increasing velocity, the viscosity, the resistance increases and the blood flow decreases. So, coming to the last slide of this very long lecture, let's see what is the effect of pressure on resistance and blood flow. From what we have discussed so far, most of you might think that if we keep on increasing the arterial pressure, we may have larger blood flow. But this is not the case, because if you remember the Ohm's law, the pressure is directly proportional to flow, but the pressure is also directly proportional to resistance. If you keep on increasing pressure, it may increase the flow to some extent, but on further increase of pressure, the resistance also increases. This increase in resistance does not allow the blood flow to increase any further. In the end, I would like to thank you for your patience and hope that this lecture was helpful for you. Thank you.